This is problem number 36 out of the textbook. It reads, a teenager pushes tangentially on a small hand-driven merry-go-round and is able to accelerate it from rest to a frequency of 15 RPM in 10 seconds. Assume the merry-go-round is a uniform disk of radius 2.5 meters and has a mass of 760 kilograms, and two children, each with a mass of 25 kilograms, sit opposite each other on the edge. Calculate the torque required to produce this acceleration, neglecting frictional torque. What force is required at the edge? So to start this problem, we have to recognize that there's going to be a resistance of rotation that is essentially an array of three different things. So I'm going to say that the total moment of inertia is going to be equal to the moment inertia of the disk itself plus the moment inertia of the two children, which I've labeled 1 and 2, if you will. I guess that's made it a little bit confusing because I've labeled it here as 2 and 3. So let me make that. Sure. Let me change that here. So this will be kid number 1 and kid number 2. And the disk has a moment of inertia of 1/2 mr squared because it can be treated like a solid cylinder. And the two kids can be treated as point masses. And since they are identical, I can just multiply twice times one of their moments of inertia as point masses, which will be m times r squared. So now I'm ready to kind of plug in some values. The total moment of inertia is equal to 1/2 times the mass of the disk, which was given to me as 760 kilograms. The radius of the disk is 2.5 meters. I have to remember to square that. And then I'm going to add to it twice the mass of one of the kids, 25 kilograms, times the radius, 2.5 meters squared, since they're sitting at the edge of the disk. When I do that, I get a total moment of inertia of 2688, or 2,688, and the units for moment of inertia are kilogram meters squared. So at this point now I have the moment of inertia of the entire system. I can find the angular acceleration because I was given information about its initial and final angular velocity. Its initial angular velocity was 0, it was at rest, and its final angular velocity was 15 revolutions per minute, which I know that I need to convert to radians per second because they're non-standard units. Using some train tracks to do that, I could basically kind of write that out right over here. And so I can say 15 revolutions in 1 minute. We know that 1 revolution is equal to 2 pi radians. And we know that 1 minute is equal to 60 seconds. So now I'm basically ready to cross out my revolutions. I can do the same thing to minutes, and I'm left with radians per second. And I get, when I put that through my calculator, I get 1.57 radians per second. So that's my converted final angular velocity. We know that the time that it takes to push the kids up to that speed is 10 seconds. That was given to me in the problem. So I'm going to use the second kinematics equation, omega final equals omega initial plus angular acceleration times time. Solving for alpha, I get omega final minus omega initial divided by time is equal to alpha, which of course can just be, when I'm ready to substitute, that becomes 1.57 radians per second minus 0 divided by 10 seconds. So now I know that my angular velocity is 0.157, 0.157, and my units are radians per second squared. So now I have both my angular acceleration and my moment of inertia. I'm going to finish this problem with a last step by recognizing that a net torque will cause an angular acceleration. I have both I and alpha, which can be substituted. So now I can basically just say, all right, well, let's take this number, plug it in for I. Let's take this number for acceleration and plug it in right here. And I'll be ready to produce an answer of a net torque when I multiply those two by each other. and I'm getting 422 meter Newton. And if I'm dealing with sig figs, I'd call that 420. And that's the answer that I'm going to basically present. If I had to answer that last little part, which was, well, what force is required to do this? I'm going to kind of draw a top view of the merry-go-round. So this is kind of the side view, if you will. The top view shows you that the force that the teenager applies is tangent to the circle. So there's the applied force, where this is the lever arm to the axis of rotation here. That would be the radius of the circle. The angle is 90 degrees if it's tangentially applied, so the theta in the torque equation, Fd sine theta, will be 90. So what I can say is then that this torque of 420 newtons is equal to Fd sine theta, where theta is 90 degrees, and so it's just going to be 1. And I know the torque and I know the distance. It's 2.5 meters. So I can basically solve for F by dividing the net torque in the system by the distance d. I'm going to take my 422 meter newtons and I'm going to divide it by 2.5 meters. And therefore my answer for torque, for the applied force is 169 newtons. Again, dealing with sig figs, I will truncate that to 170 newtons.